We're going to start with climate sciences and the irreproducibility crisis. The first speaker is Tim Edgell from Principal Environmental Service, Stantec Incorporation.
Thank you. Thank you, David, for inviting me to this. First time in Oakland. Yeah, go Raiders. I know how to get a crowd going. I'm Canadian. I know the importance of sports. And I'm not leaving here without a real man wear black shirt. I'm not an academic. I was getting a kick out of that last conversation about all these academics and what are they going to do and work in fast food. Nothing against Wendy's. I like nothing like a good bacon cheeseburger, but I'm one of those scientists that didn't work at Wendy's. Nor did I stay at a university. So my talk today is going to be about bias in science and a little pet project that me and some colleagues put together. Well, because it's about bias, and so much about bias is about people's worldview and their perspectives and their sympathies. That was a good one. I like that. I'll use that. Sympathetic biases. It's important to be open and honest about what your perspectives are and what your potential biases are. And as we go, and I go through the examples today, I'll sort of be revisiting this idea that really bias in science, and I don't see that as much of a big problem as long as you're acknowledging it and seeing how it may be influencing your outcomes and your theories. I started when I was finishing my bachelor degree as a tour boat driver. It was actually more exciting than that. I drove a 30-foot rigid hull inflatable and watched killer whales and off the coast of Vancouver Island. That whale there is about 80 years old. In a strange twist of fate, I went on from there. I ended up now as an industrial scientist, and this same population of whales that's living off the coast of Washington State and British Columbia, critically endangered, are under threat by things like tanker traffic and some of my biggest clients. I fell in love with the ocean, decided to go back to school, and ended up on the east coast of Canada working at the University of New Brunswick and Northeastern University in Boston, studying snails and the evolution of snails. And so I'm an evolutionary biologist by training. I moved back to the west coast to study snails even more, and then eventually the real pressures of life came a knock, and I got a real job in industry. And so there's some pictures here. I mean, I've worked all over, it's brought me all over the country, working in some of the remotest and hardest to reach places on Earth, including up in the Arctic Circle, mostly for oil and gas super majors. And it's brought me into pretty close contact with some incredible things that I thought I'd never see before. Nowadays, I work as an environmental assessment practitioner mostly. I design environmental effects monitoring projects. I do science for industry, coastal and offshore, all around the world. And a big part of what I do is communicating that science to community groups. Sometimes community groups with minimal amounts of literacy of any sort, let alone scientific literacy, and who have very deep and ingrained values for the world that they live in, and concerns about how industry might be affecting their values. So, which comes to my interest in science and science communication and the importance of understanding, acknowledging biases in the science that we do. So I'll just share sort of my philosophy on theory and theory building and how bias can affect these things. If we look at these, and I notice actually, no coincidence, I'm going to get to this, but this actually cover looks a lot like the graph I'm going to show with the red dots and the white dots. This red dot, may represent my body of research that I've done, let's say as an academic studying the evolution of snails, the evolutionary development of snails. And that may be one study, that might be 10 studies, it doesn't really matter. But those are the studies, and those are the studies where I've done experiments, and the outcome has been more or less in line with what I was expecting. More or less in line with prevalent theories, with this is studies that I've done that have replicated work by other people, but by replicate I mean done the same study on a different species or from a different geographic area. The red dot represents the studies I've done where I didn't quite understand the outcome, or it didn't make sense, or it couldn't make sense, or because of what my worldview, or because of prevailing theory. And the way that science works, as you go through time, whether it's you generating more and more research, or your colleagues generating more research, is that body of facts add up. And over decades and centuries, you get more and more facts adding up, and some of those facts will stay red where they don't quite fit and they don't make sense, and there's lots of reasons why that might happen that I'll get into. A theory, therefore, is a simple explanation for all of these facts, even the red dots. And as we move on, and the facts get more and more, the reality is that no human can actually retain all the facts in their head. No one is really smart enough to understand everything that's been produced. We heard about how many PhDs are being produced on an annual basis now, and I'm going to come back to that. I will replicate your argument in one of my final slides. But there are thousands of PhDs every year coming out, publishing papers, generating studies. Nobody can keep up with that. Nobody can understand all of that. And it brings me back to this quote that I love. If you think you understand quantum mechanics, you don't understand quantum mechanics. And the reality is, when theories are built and consensuses and generalizations are formed in science, it's not a group of people all looking at the same facts and agreeing to the theory that explains that same small group of facts. It's actually a combination of all of us, from all different perspectives and different worldviews, bring our own biases into each one of these groups of facts that we're capable of understanding from all over the world. And each one of us may consider only the facts that we understand and then try to apply the same simple explanation to them. And if everybody's facts can be explained by the same simple explanation, well, that's a good theory, and that theory is upheld. And sometimes we call it a consensus or a generalization. Lots of theories have been built in this way over the hundreds of years, over the centuries. And just because a theory is built doesn't mean it's going to stand forever. And and sometimes it's surprising when you look through the history of science just how short sometimes what we just have accepted as truth through our whole life has turned out to be just some recent theory that someone has proposed and that was generally accepted. And I think this is a good example here. Germ theory was only generally accepted in the 1890s. That's not that long ago. Before that, it was miasma theory, and that theory in different forms lasted for hundreds of years, and nobody could debunk it. The amount of dots, either the red dots, the black dots, was relatively small because we didn't have the tools for the measurements. We didn't have other theories to rely on. We didn't know about cells or RNA or viruses. And so it led to crazy stuff like this, where because miasma theory, which says that disease is just spread by bad air, if you're in the same room with some diseased and dying people and you're breathing that air, well, you're going to get that disease, and then you're going to be diseased and dying. And there's, in some cases, almost comically, the same theory is tried to apply to explain some of those red dots, those facts that just didn't add up. For example, why is your local baker so fat? Well, because the local baker's in the bakery smelling the air of bread and pastries all day long. True story. That's when you're trying really hard to make a theory fit some of those red dots. Think of theories like theory of special relativity. I mean, I love that one too, and that one's always been an inspiration to me. When Einstein came up with this theory, there was lots of red dots because the tools didn't even exist to measure these things. There were no particle accelerators. There was no nuclear fission. There's no Hubble telescope. And yet, now that these tools exist, and now that we can take some of those measurements, all of a sudden some of those red dots are turning black, and the theories are being upheld because these simple explanations still explain this great number of facts that keeps on growing. And there's fascinating stories with all of these theories, some based on smaller clusters of dots, others based on large clusters of dots. So what, in my mind, makes a good theory? Well, a good theory is simple. E equals mc squared. That's beautiful. Accessible. Lots of people can at least kind of understand it. Now that I say that, don't try to get me to explain special relativity. Next. We're out of time for that. And the theory explains the largest number of available facts. Now, there's an assumption there. There's an assumption that all the facts actually are available, even if you haven't found them yet or you haven't taken the time to understand them, that they're actually out there to be understood and they're not somehow tucked away. And that's going to be the central part of the second part of my talk. Good theories allow for testing through systematic observation and experimentation. That's scientific method. Good theories are inherently uncertain and open to modification. Why? Because as new facts become available, the theory needs to be able to explain them. If the theory really cannot explain them, if those facts are verified, are replicated, and come to be dependent on as true, the theory needs to be able to explain them. If it can't explain those facts, then you need to debunk the theory or modify the theory and come up with a new simple explanation. Hence the change from miasma theory to germ theory. And now we gain confidence in facts and theories when A, all available facts are considered and available and accessible. So we feel confident that we have all the information in front of us. And there's a thing that will appeal to the statisticians in the room, is that we gain confidence when sample size increases. And I put sample in brackets because sample size can be different things. Sample size can be the number of individuals you included in your study. It could be the number of studies. In that image I showed before with the dots and the ellipses, it could be each ellipse could indicate a sample of n equals 1. Each individual in this room is one sample. Your knowledge is not independent of the other knowledge in your brain. As we gain more and more of those, then a confidence will increase. So, can theory be biased? Well, of course. Most of you have the opposite of what that list I just went through. But as we heard already, academic survival requires regular publication, and there's pressures to do so. This is my postdoc supervisor, Richard Palmer, made a great observation. A simple one is that scientists do more studies than they publish. That's how Darwin started with his theory of evolution. More offspring are born than live to reproduce. And if more studies are done than are actually published, well, what happens to those other ones, and how important are those to your theory? What we see and what has been shown in the literature, there's some legal arguments for that one too, which we heard. I love it. And what we have seen and other people have done when doing literature reviews and meta-analyses is that in general there's this pattern where those red dots, those non-significant, the ones that just don't add up, the confusing, the contradictory, whether it's contradicting to your sympathetic beliefs or to some theory that's generally accepted by the wide scientific audience, those types of results are less likely to be published than the ones that sort of affirm beliefs, that affirm the theories that are inherent in our individual biases. And so the theory, the consensus, the generalization, they all assume that all known facts are available and being considered. Thank you. The good thing is that you can test for biases in the publication record, or you can test for when not all available facts are available and being considered. And this was done by my postdoc supervisor, who lured me to this. Generally, the white dots are like the red dots. Generally, these dots are less likely to be published. The ones that have low sample sizes, high variance, and not large effect sizes, those are less likely to be published. And some of the drivers for that, so on the issue of replication, is that this is part inherent in the scientific institution. If you look through instructions to authors or referees in journal pages, well, there is a push to develop new concepts, new empirical information, significant original result, new and exciting work, substantially advanced. So to be producing replicative work that is kind of similar but increasing this, the number of times you've replicated, there is a diminishing return on that. So me and my colleagues decided to apply this to the study of climate change, and we were all marine biologists, so we applied it to marine biology studies. And these were all experimental type studies of what effect under a climate change scenario, what kind of effect can we have on marine organisms? And when we looked through 1,154 experimental results from 120 articles in 31 journals, and we parsed it out and took the information we needed and plotted it out. And in fact, actually, we found no evidence of selective reporting. We found that all available facts were being reported. And in the various, and in my 5 minutes, I can't get into all the ways you can interpret a funnel graph. But the one key giveaway is that if you see big holes, especially at low sample sizes, down on this side of the graph. We then looked deeper and said, well, what if we just look at the results in the abstracts sections of journals versus what's written down in the results section, the methods and results section? You know, that section that we all read every single journal every time? Turns out, actually, there is a strong stylistic and a significant stylistic bias. And there's reasons for this. I mean, you have character limits on what you can write in the abstract. You're being instructed to put your boldest, most significant results up front. And sure enough, this shows through in the scientific literature for climate change. And it's especially true in high impact factor journals like Proceedings of the National Academy of Science and Nature and Science. Less prominent in sort of lower impact journals, the greater volume of journals that most people are reading. The danger here, in terms of are you considering all facts, is that if you're in the habit of only reading abstracts to get your science, you're going to have an inflated impression of what the true effect size or what the potential implications of climate change are. Conversely, the actual underlying theories that changes will be happening, that their effects will be had, is actually upheld and strengthened. And the only danger here is that we don't acknowledge that there's biases in how science is written. If we accept that and understand that there are biases in how scientific is written, then we can have better confidence in theories like the theory of climate change or the theory of how climate change could be affecting marine organisms. And another interesting thing from a sociological perspective is that actually rates of publication change with respect to big seminal events. So IPCC 2007, for all you climate change aficionados, as soon as that happened, with a bit of lag time, there's a big surge in publications. Not only that, if you look in the abstracts, in that period of time, there was a tendency to report the bigger effects. After ClimateGate, when the emails were stolen and put out on public record and scrutinized, well, actually, there was a dip in publication rates. And all of a sudden, maybe there's a bit more tempered way in which people were communicating their results. N equals 1. Practical solutions for scientific bias. Okay, so we're all got a role to play here. Consumers of science, that's me. I don't really do primary science anymore, I just apply it. Be a theory builder, just in general, and not just in science, but in life. Be a theory builder. Seek all available facts. Acknowledge your biases, don't pretend they don't exist, and scrutinize your truths. For universities, include formal studies for unconscious bias, stylistic bias. I never learned this stuff. I learned this stuff when I wrote this paper. I didn't learn this stuff when I was going through my doctorate or my postdoc. Reporting methods. Teach the value of replicative studies in addition to the novel free-thinking approach that we're pushed to do when we go through our graduate degrees. Demand combinations of observational and experimental studies. I think that will help with the former point. Publishers, referees, funders, create incentives for replicative studies and non-significant results. And as Rich Palmer said, why doesn't every journal have a section called replications? Make it easy for people so that you know that there's a place that your study can go. You don't just file it away in the drawer, in the file drawer effect. That's not me. Demand comprehensive methods and results so that if you want to replicate a study, you actually can. Everything's online now. You don't have to worry about page limits and character limits. Have the detailed methods online. That's easy for publishers to do. Create standards for scrutinizing meta-analysis. Whenever an editor asks me to review a meta-analysis, the first thing I look for is the funnel plot. Some final thoughts. Remember that science, this is a human construct. It's nice and make-believe to think that science is this purely objective thing, that we only seek facts. It's not true. Everything you enter in your life, you're carrying some sort of bias into it, and science is no exception. Scientists are storytellers, and in fact, we need to become better storytellers. We need to make science accessible. I still bang my head against the wall, even though I do biochemical studies. There's a point where I just can't take it. And I just, because I don't understand it, and I know I don't have the time to really become a biochemist and study it, there's going to be a limit to how big your ellipse can be and how many facts you can retain and understand. That's communication is a two-way street. Scientists can do a better job at studying, and of course, those who are reading have to read past the headlines and maybe take the time to dig a little deeper and try a little harder to understand the underlying science and limitations and biases that might be there. You know, and we've heard some, I won't say negative. I'm much more optimistic about where we are in science right now and where we're going. Here's this graph we just heard about. You know, back at the time when Watson and Crick were describing the double helix, where the US was putting out, like 5,000 or 6,000 doctorates a year, right? That was in some of our lifetimes, not mine. Nowadays, the US is putting out over 40,000 doctorates a year. This is only the US. What about Canada? What about Russia? What about China? What about India? What about Australia? Every year, the world is putting out hundreds of thousands of new PhDs, and it's hard to get a degree without at least one publication. Who's going to keep up with all that? And so in my sort of optimistic finale, despite some of the conversations we heard, and I'm sure some exciting conversation will be had over a glass of scotch later tonight, is that I don't want us to lose sight of just how much progress we're making. And as someone who actually just applies science rather than trying to create it from scratch, these are the types of projects that me and my colleagues work on every day and are working on last week and will be working on next week. We're using satellites to detect changes in vegetation around pipelines to see if pipelines are leaking. We're attaching tags to seals to watch animals move over thousands of kilometers through different biophysical regimes in the oceans. We do a lot of rare and endangered species work. We don't even need to find the things anymore. And actually, they're hard to find. You know why? Because they're rare. We just go and take a sample of water. We use eDNA and metabarcoding techniques to develop species lists and presence and absence and identify spawning habitats. We have tools. So I was on that boat when that photo was taken, and that was up near the North Pole. You want to get to on the shelf break of the Beaufort Sea? Sure, take that. That didn't exist 100 years ago. Here's one of my study sites here on the Grand Banks off Newfoundland. That study site is 300 kilometers offshore. I have ROVs, I have boats, I have staff who can do this safely in a trained way. This is what science, I'm out of time. I came all the way from Canada for this. I'm not tenured yet. Maybe I just gave up my shot. But this stuff is doable now. This stuff wasn't doable 50 years ago or 100 years ago. This is where science has brought us. So I want to see these problems. I don't believe it's a crisis. I want to see these problems as opportunities to drive innovation, to make science better. If we're going to double, triple, quadruple our staff size and our talent pool through the growing increases in doctorates entering the workforce every year, then we got to pony up and invest in more, better quality training to educate this new workforce. That's true in my business. If we go from 100 staff to 300 staff to service a project, we need to ramp up our efforts for quality management. We have to ramp up our efforts for health and safety because those things are important to doing quality work. We need the same thing now. What got us here won't get us there. And I just want to remind us how far we have come since the 1890s. It's incredible. Thank you.